So before we begin today's class, I would like to let you know that every Sunday from 2 p.m. to 5 p.m. there is a mock test conducted in NPTEL Gate portal. So you just have to open Gate NPTEL in your website, Google, and then gate.nptel.ac.in. From that, there is a bar called mock test. So every Sunday from 2 to 5, if you would attend it, it would be nice. It would be practice before your main exam. So today we'll be solving two problems on networks, electric circuits and networks. So first problem is from GATE 2021. In the given circuit, for maximum power to be delivered to RL, its value should be. So maximum power transfer theorem, you just have to keep in mind three relations. One is you have a source, impedance, and you have a load impedance. So when maximum power needs to be transferred to the load, the value of ZL is asked in maximum power transfer theorem problems. So in the first case, ZL may have resistive component and inductive or capacitive, reactive component. Similarly, the source may also have resistive and reactive component. So we have to mainly RS and XS will be given in the problem. You will have to find the value of RL or XL in order so that the load gets maximum power. So if RL and XL are variable, then to get maximum power to the load, the magnitude of RL should be same as the Thevenin resistance of the source. Similarly, the reactance of the load should be same as, the magnitude should be same as the Thevenin reactance of the source, but with a negative sign. That is, if the source is inductive, the load should be capacitive, and vice versa for the maximum power to be transferred to the load. So this is a general case. This is the first case which you should remember in maximum power transfer theorem. The second case is there is RL and XL in the load, but you can only vary RL. Or the source has resistance and reactive. It may be inductive or capacitive, and the load has only resistance. So in both these cases, the value of RL should be root of R Thevenin square plus X Thevenin plus XL square, where R Thevenin and X Thevenin are the Thevenin resistance and reactance of the source, and XL is the reactance of the load. So this is the second case of maximum power transfer theorem. And the third case is only RL is there, XL is not there. This is same as case 2 only with XL equal to 0. So what will be your load resistance? It will be root of R Thevenin square plus X Thevenin square, which is nothing but magnitude of Z Thevenin. So these are the three cases of maximum power transfer theorem. Only you have to learn these three cases. Then you can solve maximum power transfer theorem problems. So in the given question, your load resistance is only a resistance part. Load impedance has only resistance. There is no reactance. But your source has both resistance and reactance. So this is case 3. So for maximum power transfer theorem, what should be the value of RL? It is magnitude of Thevenin impedance. So in this problem, you just have to find, in this problem, you just have to find the Thevenin impedance of the circuit. Till this part, is it clear? Or should I explain once more the three cases? Rather than studying this equations as such, it would be better if you could derive these relations. How you derive these relations is, you know that through the load, the power is I square R. You get an equation for I in terms of voltage by impedance. You get the magnitude, you find the magnitude of I, you square it. This is the power. So for maximum power, dP by d, what you are varying. If you are varying RL, dP by dRL equal to 0, you find and you get these relations. Okay. So in this problem, there is only RL. So you have to find the Thevenin impedance. If you get the magnitude of the impedance, that value will be the RL value for maximum power transfer theorem. Maximum power transfer. So when you find the Thevenin impedance, you will remove the active part, across whichever terminals you have to find. So this is A and B. You have to remove whatever the load connected to A and B, and you have to look from A and B what is the impedance you see, that is the Thevenin impedance. So to find Thevenin impedance, you have to replace all the active components with short circuit or open circuit. If it is current source, you have to open circuit. If it is voltage source, you have to short circuit. So there is an inductance. This is a voltage source, so we will short circuit it. Then there is a capacitance. There is a resistance. So for those who joined later I have to tell you that in GATE NPTEL portal, every Sunday from 2 to 5 p.m. there is mock test being conducted. So did you get the date of GATE exam?
No, ma'am. Yes, ma'am. 5 Feb. Electrical.
Okay. So till 5th Feb, all the Sundays, it would be better if you could able to attend the session, which is a mock test. So I hope you are doing other mock tests also from maybe CAs. But on top of that, it would be better if you are doing this, because this is free. So you can attend these exams. Okay. So in the problem, we are given the frequency and we have two reactive components. Now you can find the impedance of that components. There is an inductor, its value is L. The impedance is J omega L, where omega is given in the problem as 1000 radian per second. So this reactance is J, 1000 L is 4 millihenry. Milli means 10 raised to minus 3, which is 4J. Similarly, for the capacitor, the capacitance is 0.5 millifarad. The capacitance impedance is 1 by J omega C. So this is 1 by J, 1000, C is 0.5 millifarad. So this is minus 2J. So you have 4J minus 2J, and this is 2 ohm. So Z Thevenin is the impedance across these terminals. So 4J in series with minus 2J, the total impedance is 2J. In parallel with 2, parallel rule, which is 2 times 2J by 2 plus 2J. Which comes out to be 1 plus J. So this is your Z Thevenin. So this is a complex number. Your load is only a resistance. So resistance can never have a complex part. So you find the magnitude of Z Thevenin, which is root of 1 square plus 1 square, which is root 2, or 1.414 is the answer. Is this clear? Yes, round off to 2 decimal places means 1.41 is the answer. Okay, we move on to the next question. A three-phase balanced voltage is applied to the load shown. The phase sequence is R by B. The ratio of magnitude of IB by magnitude of IR is. So every three-phase circuits, it would be better if you know the phasor representation. You have phase sequence R by B. So your voltage VR will come first. If my rotation I am considering, phasors are rotating in this direction, then my Y phase will come 120 degree lagging VR. and my B phase will further lag Vy by 120 degrees. So this is my Vb. So when you draw the phasor diagram, you have to keep in mind the direction of rotation. So first Vr will go, then Vy will come, then Vb will come. So that is my phase sequence. So a three-phase balanced voltage. This is a balanced voltage is applied. Phase sequence is given. The ratio of the currents is asked. So this is your Vr. This is your Vb. This is your Vy. If I am grounding this terminal, the potential at this point is Vr. The potential at this point is Vb. The potential at this point is Vy. So what is the potential across minus J10? It is Vr minus Vb. Is there any doubt on that? Because this Vb is same as this potential here. This is Vb.
Clear, ma'am.
Okay. So Vr minus Vb is the potential across minus J10 ohm. So your IR is Vr minus Vb by minus J10. Vr minus Vb is nothing but Vrb by minus J10. So in the phasor diagram, what is Vrb? Vr you already know. Minus Vb is same as plus minus Vb. It is a sum of two vectors. One is Vr, other is minus Vb. So Vb is in this direction, which is 120 degree from Vr. So minus Vb will be 180 degree displaced from Vb. So this is minus Vb. So now you are performing vector addition. You have to add Vr and minus Vb. Addition means use parallelogram vector addition. So Vr plus minus Vb will be, this is your Vrb. Now since the magnitudes of all these vectors are equal, if this is 120 degree, the angle between Vr and minus Vb will be 60 degree. Also magnitude of Vr and minus Vb are same. So their sum will be, Vrb will be displaced from Vr as well as minus Vb by the same angle. So this angle and this angle are same, which is nothing but 30 degree. So if Vr is V phase magnitude angle 0, then what is Vrb? It will be root 3 times V phase. The magnitude will be root 3 times V phase. Angle will be minus 30, which you can see from the phasor diagram. Is everyone clear with how we got minus 30?
Yes, ma'am.
Okay. So root 3 V phase, I am writing it as VL. So it is VL my angle minus 30. So IR, this is vector. All these are vectors. So vector IR is VL angle minus 30 divided by minus J is minus 90 degree. You know, this is real part, this is J. This is 1, this is J. This is minus 1, this is minus J. So minus J is minus 90 degree. So this is 10 angle minus 90 degree. Or VL by 10 angle. Division of two angles will be subtraction. Say one angle A by one angle B is one angle A minus B. So this is VL by 10 angle minus 30 minus of minus 90, which is VL by 10 angle 60 degree. So your IR vector is VL by 10 angle 60 degree. Now we have to find IB. IR we already found, IB we have to find. We don't have any impedance. We cannot write IB as a voltage by current impedance form. So what we will do, we will make use of Kirchhoff's current law. The sum of currents entering the node is 0. So the sum of IR, IB and IY are entering the node. So IR plus IY plus IB is 0, or IB is minus IR minus IY. So you already have IR. You have to find IY. IY similar to IR. IY is the voltage across J10 by J10. So IY direction is this. So this potential is Vy. This potential is Vb. So IY is Vy minus Vb by J10, which is nothing but Iy is Vyb by J10. So Vyb you can get from the phasor. This is your R, this is your Y, this is your B. Vyb is Vy plus minus Vb. So Vb minus Vb is here, which is 60 degree from both Vr and Vy. So parallelogram addition of vectors, this is your Vyb, which is 30 degree from both the vectors. So from Vr, Vyb is 90 degree. So when you write in terms of Vr is your reference. So it will be line voltage angle minus 90 degree by J is 90 degree. So this is VL by 10 angle minus 180 degree, which is Iy. So now you have IR and Iy. So your IB is minus VL by 10 angle minus 180 minus VL by 10 angle 60. So this is VL by 10 minus 1 angle minus 180 and plus 180 are same. Minus 180 means this point, plus 180 means you will rotate in the same direction of the vector rotation. So minus 1 angle 60. So this is VL by 10. If you put in the calculator, you will get it as 1 angle minus 60. So the magnitude ratio is asked. Magnitude of IB is VL by 10 and magnitude of IR is same, VL by 10. So the magnitudes ratio of the magnitudes of the currents is 1, which is the answer. Is this clear?
Yes, ma'am.
Okay. So that's a wrap of today's session. We will meet on next Thursday. If there are any more doubts, if anyone has, you can ask.
Ma'am,
Yeah.
can you say about which topic you proceed, ma'am?
I didn't understand your question.
Ma'am, which topic you taught, ma'am? Which topic under the problem, ma'am?
No, I didn't understand your question. Can you be specific?
Which concept you taught, ma'am?
In where teaching where?
This
Ma'am, he's asking about the topic you are teaching us. Is it?
Today it was given networks, electric networks, circuits and networks is today's session. The topics for every days will be given in the gate portal.
No, ma'am. In
Whichever-
electric machines, which topic, ma'am?
I am working on.
No, ma'am. In electric machine, which topic you taught? No, ma'am.
He's asking about in networks. Which topic is this network question?
Okay. This is on three-phase